In section 2.3, we're going to be learning about functions. Now, in order to talk about functions, first thing we have to do is talk about a relation. What a relation is it's a way to show how two variables coincide. I don't want to say are related because that's using the word in the definition, but coincide means how they affect each other. For example, the more food I eat, the more I weigh. The more I lift weights, my maximum bench press goes up, something like that. Now we have different ways we could show a relation. One way we could show a relation is with a table. And a table just looks like this. You could have x and y values, maybe as x is like 1, 2, 3, 4. To get y, you just multiply by 2. We could also have an ordered pair. Now if we look at the table, the ordered pair would be like 1, 2, 2, 4, 3, 6, and 4, 8. Generally, we talk about like a set of ordered pairs, so we write it inside of curly brackets. Another way we could show is using a graph. And it looks like y would equal 2x. So the graph of y is equal to 2x starts at 0, 0, goes up 2 over 1. That would be a graph of what those points would look like. We could also have an equation. So y would equal 2x. And the last thing we could have is something called a mapping diagram. Maybe I'll draw it over here. Mapping diagram would look like this. Where we have 1, 2, 3, 4. Those are our x values, also called the domain. And then we have range, or y values. And those would be 2, 4, 6, 8. And we could just kind of draw lines like this, like when x is 1, y is 2. 2 goes to 4, 3 goes to 6, and 4 goes to 8. This will come more into play when we talk about a function. When we're talking about a function is a relation where every x, or domain value, has only one y value, or range. That's what a function means. Let me just be consistent here. So y is the same thing as range. And then we have value over here, just like with the x's. Okay, so there's a couple different ways we could determine whether something's a function or not. One way to determine it is that no x value can have more than one y value. Usually when I'm teaching this, I draw like 1x goes to 1y. That's an easy way to remember. If you have 1x going to 2y, that's no good. And the second way we could do this is if we look at graphs. we could use what's called the vertical line test. We're drawing a vertical line through a graph, only touches in one location. So for example, if I had a graph like this, maybe a graph like this, and a graph like this. If we drew vertical lines through these graphs, well, it only touches in one place here, so we'll call this a function. fxn is abbreviated function. Same thing here. We draw a vertical line, it only touches in one place, so we'll call this a function. Clearly, if we draw a vertical line here, this is not a function because it crosses in more than one place. So we say it fails the vertical line test. Okay, so now let's move on and let's state the domain, range, and determine if it's a function. Okay, let's start with something like this. Curly brackets, goes 0, 1, 1, 1, and 2, 3. Domain, range, and is it a function, yes or no? Okay, well the domain, usually we list domain and range values from least to greatest. So this would just be 0, 1, and 2. Range values, again, from least to greatest. You don't want to repeat 1. It's what could be a possible y value? The answer is 1. It's not 1 and 1. It's 1, 3. And is this a function? Does every x value only go to one y value? So does 0 only go to 1? Yeah. Does 1 only go to 1? Yeah. Does 2 only go to 3? Yeah. The y value could repeat. X value is not allowed to repeat. If we were to see this, maybe in a mapping diagram, draw the domain, we'll draw the range. 0, all the x values are only allowed to go to one y value. So 0 only goes to 1. 1 only goes to 1. 2 goes to 3. So the answer is yes, this is a function. What if we had a problem like this? Let's say we had 2, 1, 3, 2, and 2, 5. Okay, well the domain would be 2, 3, and 2, so we're just going to write 2 and 3. Range would be 1, 2, 5. And is this a function? No, because you see how 2 goes to 1, but it also goes to 5, so that's not allowed. If we saw this in a mapping diagram, 2 would go to 1, but 2 would also go to 5, and that's the problem right here. So that would not be a function. What about just if we had mapping diagrams? Like what if we had what if we had 1 and 2 both going to 3? Well, the domain is easy, it's 1 and 2. Range is easy, it's just 3. Is this a function? Is 1 only going to one number? The answer is yes. Is 2 only going to one number? Yeah. They're both the same number, but that's okay, as long as every x value is only going to one y value. What about if we switched it, like if we had 1 and 2? The domain would be 1. The range would be 1 and 2. Now, is this a function? No, because you see how 1's going to 1 and it's also going to 2. So that's why it's not a function. What about a problem like this? X is equal to the absolute value of y. And that's all we know. So that's an equation. Let's see if it could be a function or not. Now, we don't have anything that tells us what the domain is, so we could pick any number you want. That's why the domain would be all real. Well, would it be all real numbers? I'm not sure. Let's think about this a little bit more. Could x be 0? Yeah, if x was 0, y would equal 0. Could x be 2? Yeah, I mean, the absolute value of y is equal to 2 means that y could equal 2 or y could equal negative 2. Could x be negative 2? Well, absolute value can't be negative, so it looks like the domain would be any number that's greater than or equal to 0. What about the range? Well, you could see how this is going negative 2 and positive 2, right? So 0. So a rough sketch of this graph, if we start at 0, the absolute value of 2 would look like this. We get a graph that kind of looks like this. The more points we pick, we could see that this is happening. The range would actually be infinite, right? Any negative value, because this goes on for forever, up to any positive value. So is this a function? Well, look at the graph. No, right? It fails the vertical line test. Also, right here, we put when x is 2 in, and we got 2 y values. So that's like a big no-no. That doesn't work. How about y is equal to the square root of x? Can you plug 0 in? Yeah. Can you plug 1 in? Yeah. Can you plug 2 in? Well, square root of 2 is not a nice number, but you could take the square root of it. Could you plug in negative 2? No. So square root's kind of similar to the last problem we saw, where we could use any number starting at 0 up to infinity. The square root is never going to give you a number less than 0. And actually, we'll talk about this in an upcoming lesson. The graph of the square root function looks something like that. So the range is always going to be 0 or higher than that. And by looking at the graph, is it a function? The answer is yes. It passes the vertical line test. What about a circle? What if we had just, say we had x squared plus y squared is equal to 9. Well, center would be 0, 0. Radius is 3. So what are possible x values? Well, it goes from negative 3 to positive 3. Possible range values, positive to negative 3. Is it a function? No way, right? Because if you draw a vertical line, it would touch in more than one place. We'll see one more. Soon we'll be talking about trigonometry. And in trigonometry, we have the graph of what's called sine. And I don't expect you to know this right now, but let's just look at the graph of sine. It'll look something like this. And it just kind of keeps oscillating like that. The highest it goes is 1, the lowest it goes is negative 1. That tells you the range. The domain, it looks like it just keeps going on for forever, right? And is it a function? Yeah, because you could draw a vertical line and it only touches in one place. talk a little bit more about domain, range, and whether it's a function. Now, when we start looking at these kind of problems, there's really two main domain restrictions. All right. So when you have a denominator, it can't be 0. So we have to keep that in mind. Also, when we have a radical, whenever you take the square root of something, it's always going to give you a number that's greater than or equal to 0. So let's take a look at a few examples like this. So what if I gave you the graph y is equal to 1 over x? Do you see a denominator? Yeah, x, right? So x is not allowed to be 0. Do you see any other restrictions? I mean, is there a radical there? The answer is no, right? So as far as what the domain would be any x value except 0. So the way that we would write that is we would say it's from negative infinity to 0, not including 0, in union with 0 to positive infinity. This is the way that we could say any number, just not including 0. As far as what the range would be, the range for these are going to get a little bit tricky. We're going to dive more into this when we talk about graphing rational functions. But the range for this would be from negative infinity to 0 also, and then from 0 to infinity. We actually have asymptotes with this graph, and this would be a function. If you pick any x value, you're only going to get one y value. What about a problem like this? Y is equal to the square root of 2x plus 1. Now we said for our second restriction, what's inside the radical is always going to be greater than or equal to 0. So the way that we find the domain here is what's inside the radical. We set that greater than or equal to 0. You can't take the square root of a negative. You get an imaginary number. So this would be 2x is greater than or equal to negative 1. X is greater than or equal to negative 1/2. So in interval notation, we would write negative 1/2 to infinity. As far as what the range of this would look like, we'll learn about these kind of graphs a little bit later on. This graph looks just like our regular square root graph, except it's a little stretched and it's moved to the left a little bit. It's moved to the left actually half a unit. The graph would look something like this. So from looking at the graph, it looks like the range would be from 0 to positive infinity, and it is a function. Passes the vertical line test. One more. What if we did a combination? Let's say y is equal to 1 over x plus 1 inside of a square root. Well, first domain test, remember we have two, right? Is there a denominator and is there a radical? The answer is yes, there's both. So for the domain, we have to take care of both, right? One thing we have to make sure is when is x plus 1 equal to 0? And then we're going to say that that's not going to be an answer. If you square both sides, subtract 1, you get x can't be negative 1. Something else is we do have a radical, so second thing we have to do is we say what's inside the radical has to be greater than or equal to 0. So x plus 1 has to be greater than or equal to 0, so x is greater than or equal to negative 1. So let's combine these on a number line. Looks like negative 1 is our number. It can't be negative 1, and it has to be greater than or equal to. So let's compromise and say any number not including negative 1, but greater than it. We would list the domain here as negative 1 to positive infinity. the range is going to be a little bit trickier. You wouldn't actually be expected to know this. So let's just kind of say to be determined, dbd. And then is this a function? Well, if you plug in any of your domain values, you're only going to get one y. It's not like you're going to get plus or minus. So the answer is yes. You will always get one y value for every x value that you plug in. Let's move on to something a little bit different. You might have seen the notation f parentheses x. This just means that the relation is a function. And it's read f of x, or function of x. So instead of saying like y is equal to x plus 1, which is a line, y-intercept is 1, slope is 1, up 1 over 1. It's a function, right? So let's just say f of x. If you say f of x, that's telling the interpreter or the reader that you know that it's a function. Next, I'd like us to evaluate if f of x is equal to negative x squared plus 5x minus 3. And let's say g of x. So f of x is an equation. It's the same thing as saying just y equals, right? But f of x gives us more information. And g of x is just going to be a graph. Let's let the graph look like this. Okay? So if I asked you to evaluate f of negative 1, well, I know what f is. F is this, right? This is the function f of x. If I ask you to evaluate f of negative 1, that means that everywhere you see x, we're going to put negative 1. It's asking you, what's y when x is equal to negative 1? That's what this is asking us. So let's plug in negative 1 and let's see. So we get negative 1 minus 5 is negative 6, minus 9 is, let me see, did I do that right? So negative 1 minus 5 is negative 6, negative 6 minus 3 is negative 9. That's how you do a problem like that. Eventually we'll be getting to some more complicated problems where I might ask you what's f of x plus 1. That's going to come in handy when we talk about a difference quotient, when we talk about composite functions. But this is the same thing. I mean, the rule is that anything inside parentheses, we're going to plug that in instead of x. We're going to say negative x plus 1 squared plus 5 times x plus 1 minus 3. So this would be negative x plus 1 times x plus 1 plus 5x plus 5. Let's distribute x plus 1 times x plus 1. We'll distribute this negative. So it's not really hard, and it's just the notation that could be a little tricky to understand. Negative 2 plus 5 is 3x, negative 1 plus 2 is 1. That would be our answer. Last problem I want to do is like a little bit different. What if I asked you, what's g of 0? Well, remember what we said over here. Really, the question's asking you, what's the y value when x equals 0? Okay, well, x equals 0 is right here. And what's the y value there? Well, we have this point, right? That point would be 0, 2. So when x is 0, the y value is 2. We just have to interpret the graph to get that answer. Last part from this section, we'll just be talking a little bit more about vocabulary. When we say that a graph is increasing, that means we're reading the graph from left to right. And really what this means is as x increases, y increases. And this means we read the graph from left to right. That would mean the graph looks like this. The graph's going up from left to right. We could also say a graph is decreasing. We always read graphs from left to right, just like if you were reading a book. As x increases, y decreases. So the graph is going down. And if a graph is constant, we always read the graph from left to right. What that means, as x increases, y stays the same. So this graph would be like a flat line like this. Okay, so I'll give you a graph, and what I'm going to ask you to do is describe the intervals. So we're going to be using interval notation, where the graph increases, decreases, or remains constant. So let me come up with a graph here. And I'll put a point maybe at -3. I'll just put some points for my own reference. All right, so let's say that that's what our graph looks like. Technically, this is called a piecewise function. You don't have to know this, but that's what it's called. It looks like the graph was made in pieces. So let's talk about where our graph is increasing, decreasing, and constant. Okay, so it's increasing from left to right. Just kind of trace it. Well, this is going down, but it starts going up right here. Then it reaches a point. So that interval, when we're naming that interval we use x values. Looks like it's from -2 to, let's see, it's not exact, but I'll put it right here, to +2. The graph looks like it's increasing. We always use open intervals when we're describing increasing, decreasing, or constant. When's the graph going down from left to right? Okay, well, looks like if we start here, the graph's going down. And then right here, the graph looks like it's going down. Just do a little color coordinating so you know what parts of the graph correspond with our intervals. And let's answer the question. So it looks like the graph is decreasing. Well, this arrow means it happens from forever, right? So it goes up for forever. So let's say from negative infinity up until negative 2. But then it starts again at 3. From 3 on, the graph is decreasing, giving us the only area that looks like it's constant. The only area that looks like it's constant is between 2 and 3. Now, as you notice, I didn't write any of the x value or any of the y values, right? When we're talking about intervals, this just means x values.